Hello everyone. This video covers the fundamentals of trigonometric inverses with regard to inverse sine, inverse cosine, and a little bit of inverse tangent. We're going to talk about the functions and domain restriction in this video. Please see the other supplemental video in the Schoology folder for the graphing of inverse sine, inverse cosine, and inverse tangent. So let's get started. Inverse functions. So way back when we started talking about inverse functions, we talked about how if a function is only a function if it passes the vertical line test. So if we had, for instance, y equals x squared plus 1, if we were to pass a vertical line through it at any point, we would only ever hit the function once, which would indicate that it is a proper function. Whereas to talk about our inverses, we would take a horizontal line, the horizontal line test, and write it horizontally. If we hit the function only once, then we had a proper inverse. If we hit it more than once, we did not have a proper inverse. In this case, the graph of x squared plus 1 does not have a proper inverse because the horizontal line test hits it twice. We're going to run into that same sort of function with regard to some of our trig functions. As mentioned during the initial graphing of cosine notes, our trig functions go on infinitely in both the positive x direction and the negative x direction. Any horizontal line we draw is going to hit the graph an infinite amount of times. Therefore, in order to make an inverse function for our trig functions, we must restrict our domain so that the inverse is a proper function. In this case, for cosine, we're restricting it from 0 to pi, inclusive. So here's our restricted domain. Like I said, the other video has how we would graph this, but the fundamentals of graphing are the same. We would swap our x and y components for each point and plot those out. Now, with regard to our cosine function, this function will now pass our horizontal line test and therefore has a proper inverse. But that inverse will be restricted to the domain of 0, 0 pi, inclusive, and for good measure, our restricted domain also has a range of -1 to 1, also inclusive. When we look at the inverse, we're basically swapping our domain for our range. So, the equation for an inverse of y equals cosine x is obtained by interchanging the x and the y, old information, leading to the equation x equals cosine y, which, when we take the inverse of, gives the common notation of y equals cosine inverse of x. Now, sometimes you're going to see this written as arc cos. That's okay. There's debate in mathematics as to what's more appropriate, the arc prefix or the -1 exponent. They're both the same thing. The Desmos calculator that I've linked to you in the course page uses the exponent version, but some calculators that you might find on your own or use on your own might have arc cos. They both mean the same thing. Fundamentally, we read it as y is the angle or real number whose cosine value equals x. Now, all of the values that we have are going to be along the interval of 0 to pi, because that is our domain restriction. If it's not in 0 to pi, then we're going to have to get a little creative. Let's look at some examples. So we want to find the exact value of each of the following. Firstly, cosine inverse of 0, also known as for what theta do we have a cosine inverse of 0? Well, if we consult our unit circle, we're going to see that our theta must equal pi over 2. Cosine inverse of -1, or theta equals the cosine inverse of -1. If you consult our unit circle, this is going to occur at theta equals pi. Theta equals the cosine inverse of negative root 3 over 2. This will occur at 5 pi over 6. And theta equals inverse cosine of root 2 over 2. This will occur at pi over 4. So all of our examples in this case, given a unit circle sketch, all ran from 0 to pi in our restricted domain. No need for us to get creative. Maybe we'll get creative for sines. So, sine function, same sort of thing. Our sine function fails our horizontal line test because it extends infinitely in the positive x and infinitely in the negative x. So we have to restrict its domain as well. Except this restriction is going to be a little different. We're not going from 0 to pi, rather we're going from negative pi over 2 to positive pi over 2. So we have our slightly different restriction. However, our range is still going to be the same. We still have the range from -1 to 1, fully inclusive. And because we've restricted the domain, it now passes the horizontal line test, meaning that it has a proper inverse. As mentioned, please look at the other video for graphing of this inverse. Other than that, it follows the exact same rules as our inverse cosine. We're basically looking for, we swap our x and y, we take our inverse to give us y equals inverse sine of x. And once more, you might see this as arc sine of x. That's fine. Arc sine and sine inverse are the same thing. As far as interpretation, it's the exact same interpretation. Y is going to be the angle or real number whose sine value equals x. Except now, all our answers will be on the interval of negative pi over 2 to pi over 2. Unit circle sketch. That means all of our answers are going to run from negative pi over 2 all the way over to pi over 2. And I know, some of you might be thinking, wait, that down there, that's not negative pi over 2, that's actually 3 pi over 2. Well, you're right. But it's 3 pi over 2, and it's negative pi over 2. Because as mentioned back in January, our unit circle runs from 0 all the way around to pi. So if we have 2 pi over here, and we subtract from it pi over 2, well, that's going to put us into, once we turn it into an appropriate fraction, 2 pi is the same as 4 pi over 2. 4 pi over 2 minus pi over 2 is equal to 3 pi over 2. So both 3 pi over 2 and negative pi over 2 are the same position down here. And this is where things might get interesting. If we end up having values that are outside of this restricted domain, we might need to get creative and use negative radian values to find a more appropriate value. So, we want to find the exact values of the following. Once more, sketch of our unit circle. We have a restricted domain to work with. We're basically working off of quadrants 4 and 1. We want the sine inverse of 1. Well, that's going to occur at pi over 2. The sine inverse of 1/2, that'll occur at pi over 6. Both of these values are still within the restricted domain of negative pi over 2 to pi over 2. But this next one isn't. We want the inverse sine of negative root 3 over 2. Now, negative root 3 over 2 occurs in two places. It occurs down here at 4 pi over 3, and it occurs right here at 5 pi over 3. Now, I know what you might be thinking. 5 pi over 3, that's inside of our desired quadrant 4. Therefore, it must be 5 pi over 3. But here's the thing. 5 pi over 3 is greater than our restricted domain of pi over 2. Because our restricted domain runs from negative pi over 2 to pi over 2. Therefore, we can't have it written as 5 pi over 3. Rather, we need to, instead of going counterclockwise for our radians, we need to go clockwise and use our negative radians. So, in order for us to go from our 2 pi down to 5 pi over 3, we essentially have to go negative pi over 3 units. Negative pi over 3 fits within our established domain of negative pi over 2 to pi over 2. Therefore, our answer will be negative pi over 3, not 5 pi over 3, because that's too big. They are essentially the same measurement, but the negative pi over 3 fits within our restricted domain. The 5 pi over 3 does not. All right, same sort of thing here for inverse sine of root 2 over 2. Negative root 2 over 2 occurs in two places. It occurs over here in quadrant 3 at 5 pi over 4. It occurs here in quadrant 4 at 7 pi over 4. But here's the thing though, 7 pi over 4 is too big. So rather, how do we go from 2 pi down to 7 pi over 4? We get there by subtracting pi over 4 units. They're both the same measurement, but this measurement falls within our restricted domain. I know, that's a little weird. With practice, it'll make more sense. All right, so the remaining trig inverses. All the remaining trig inverses follow a similar pattern. Now, for the most part, the other video also goes into how to graph inverse tangent. I'm not going to go into graphing inverse cosecant or inverse secant or inverse cotangent, simply because I didn't ask you to learn the normal graphs, so I'm not going to ask you to learn the inverse graphs. We will see these sorts of things again in problems, but more on that next week, essentially. And I'll work some of those problems next week. Now, along with inverses, way back when, we also talked about compound functions. Compound functions were when we had multiple functions occurring in the same equation. So you had things way back when, like f of g of x. And as we did way back when, we always solved our innermost stuff first, and then used the output from the inner stuff, become the input for the larger stuff, and solve that way. We're going to do the same sort of thing. We'll work with the innermost parentheses first, and then work our way out. The only thing that's going to be slightly different now is we're using trig functions, and we have to pay attention to any potential domain restrictions. So, let's take a look at our example. Right off the bat, we have a inverse cosine. That inverse cosine means we're going to have a domain restriction from 0 to pi. So whatever value we end up having is going to have to exist within our domain restriction of 0 to pi. All right, so let's work from the inside out. Our innermost thing here is sine of 5 pi over 4. Consulting our unit circle, 5 pi over 4, the sine of this is negative root 2 over 2. So our problem now becomes, what is the cosine inverse of negative root 2 over 2? The cosine inverse of negative root 2 over 2 is going to occur at 3 pi over 4. So if you recall, cosines deal with our x components, our adjacent sides. Negative root 3 over 2, negative root 2 over 2 is going to occur over here in quadrant 2 at the, what is essentially the 45-degree angle, or the 135-degree angle in quadrant 2, to give us 3 pi over 4. 3 pi over 4 fits within our 0 to pi domain restriction, so 3 pi over 4 is our proper answer. If you have questions on these, please ask. Otherwise, please work on the problems in the folder.